In the upcoming video, I will provide a comprehensive overview of wind energy components and their intricate mechanical design. We will explore the various elements that make up wind energy systems and delve into the detailed engineering that goes into their design and construction. This discussion will encompass not only the components themselves but also the principles and considerations that underpin their effectiveness in harnessing the power of the wind to generate clean and sustainable energy. What is wind? Air in motion. Air has mass. The weight of air is a little more than 1 kilogram per cubic meter. Wind has kinetic energy. Kinetic energy is converted into electrical or mechanical energy. Wind energy comes from the sun. It is true, wind energy is simply a converted form of solar energy. The sun's radiation warms different parts of the earth, oceans, and other bodies of water, at different rates. The night and day cycles make an obvious difference, but also, water and land absorb or reflect sunlight differently. The result of this uneven heating is atmospheric change. Hot air rises, leaving decreased atmospheric pressure near the Earth's surface, and cool air is drawn in to replace it. The result of this air exchange is wind. How wind moves: basically, an object that has high specific heat capacity requires lots of energy to make it hotter, while an object that has low specific heat capacity doesn't require much at all. Therefore, if you apply the same amount of energy to an object with high SHC and one with low SHC, the high SHC object won't heat up much, while the low SHC will heat up a lot. In case of sea breeze, land has a low specific heat capacity than sea. Faster increase in temperature, i.e. land is warmer than sea, air above the land is heated up and rises, cooler air from the sea moves from towards the land as sea breeze. In case of land breeze, at night, the heat is lost from the land and sea. Sea has a larger specific heat capacity, so sea is hotter than land. Hot air above the sea rises, cooler air from the land moves towards the sea and land breeze. Difference between windmills and wind turbines. Wind turbines convert the kinetic energy of wind energy into mechanical power. If the mechanical energy is used to produce electricity, the device may be called a wind generator. Wind turbines, on the other hand, have fewer blades, spin at higher RPMs and produce electricity. If the mechanical energy is used to drive machinery, such as for grinding grain or pumping water, the device is called a windmill or wind pump. They have more blades that produce more torque, which is required to pump water or grind grain. Modern wind turbines, in case of stand-alone system, mostly used in remote areas, for need of small communities or single consumer. As wind is not steady, hybrid system with backup from solar or diesel generator is used. In case of connected with grid, feed power to utilities, own transformers, transmission lines and substations. Top wind power countries. The United States and China are indeed the top two wind power countries, collectively representing more than 1/3 of the world's total installed wind power capacity. Their significant contributions to the global wind energy sector demonstrate their commitment to renewable energy and sustainability. The fundamental concept of wind energy revolves around the conversion of the wind's kinetic energy into electricity or other usable forms of energy. Wind turbines, which exhibit a wide range of sizes, operate on the same underlying principle, with an identical general configuration consisting of the rotor, drivetrain, and generator. A simplified flow diagram of a wind energy conversion system, WECS, illustrates how wind interacts with the rotor, and the resulting rotational motion is transmitted through the drivetrain to the generator, ultimately producing electrical energy. Modern wind turbines. Modern wind turbines range in size from a few watts to megawatts, with the industry trend favoring larger units of several megawatts to reduce the unit cost of wind-generated electricity. They operate efficiently across a wide range of wind speeds, from 3 to 25 meters per second, and modern wind technology is adaptable to diverse sites, including those with low and high wind speeds in various environments. Wind farms, consisting of clusters of turbines, have gained widespread public acceptance due to their high availability and integration with the grid. Modern wind turbines are driven by key design factors, including reliability, grid compatibility, noise reduction, maximum aerodynamic efficiency, high productivity in low wind speeds, and the expanding offshore capabilities. The main components of a wind turbine are blades, hub, nacelle, tower. The basic components of a wind turbine system include a set of 3 rotor blades rotating around a hub. The hub is connected to a gearbox and generator located inside the nacelle, which houses the electrical components. Basic components of a wind turbine system, from rotor to foundations, are nacelle, rotor blades, gearbox, direct drives, brake, controller, generator, yaw mechanism, tower, base. The nacelle, perched atop the tower, houses essential components, including electrical components, a gearbox, brakes, an anemometer for wind speed measurement, sensors, a yaw mechanism, and a generator. Rotor blades. Blade length is crucial element in the turbine power. The greater the length of blade, the greater will be the power output. Their design and material used in their construction are also key element. Blades are generally made of fiberglass reinforced with polyester, carbon glass hybrid, etc. Typically blades rotate 10 to 30 revolutions per minute, either at constant speed or at a variable speed. Gearbox direct drives. Most of the wind turbines uses gearbox. Basic function of the gearbox is to increase the rotational speed to a level required by the generator. Some new technologies are exploring direct drives generators to dispense the expensive gearbox. Brakes, a disc used to stop the rotor blades in emergencies to ensure the safety of the wind turbine. This is applied in case of very high damaging winds or other exceptional situations. Controller, a set of electrical components that controls the starting, the stopping and the turbine rotor blade speed. Typically in the constant wind speed model, the controller starts up the turbine at wind speed around 8 to 14 miles per hour and stops the machine at around 55 miles per hour, to avoid the damage caused by the turbulent or high winds. Generator, the device responsible for the production of 60-cycle alternating current. Small wind turbines are equipped with DC generators. Large commercial wind turbines uses 3-phase AC generators, synchronous generator, asynchronous generator. Yaw mechanism, the yaw mechanism is responsible for orienting the wind turbine to face the wind. There are 2 methods, active yaw, which uses an anemometer to guide the rotor, and passive yaw, common in small turbines, where wind forces direct the rotor. Some downwind turbines employ tail vanes for alignment. Tower, supports the nacelle and rotor at desired height. Wind increases with height. The more the tower height, there will be more production, reduced turbulent air at height. The electricity produced by the generator comes down by cables inside the tower and passes through a transformer into the grid system. Base, large turbines are built on a concrete base foundations. When a wind turbine ceases production, it is a simple task to dig these out or cover them, leaving little trace behind. The base must be designed carefully by considering the local soil conditions. Turbines constantly improving. Turbines are constantly improving, with larger sizes, specialized blade designs, power electronics, computer modeling, manufacturing enhancements, and recent capacity enhancements, all contributing to more efficient wind energy generation. Classification of wind turbines. Installed location. Wind turbines are classified based on their installed location, with 2 primary types: onshore wind farms, which are constructed on land, and offshore wind farms, which are situated in bodies of water. These installations are typically organized in groups, with hundreds of turbines across vast areas, to generate significant electricity. Classification of wind turbines. Rating. Wind turbines come in various scales based on their power rating. Small turbines, with a power rating of less than 10 kilowatts, are suitable for homes, farms, and remote areas. Intermediate-sized turbines, ranging from 10 kilowatts to 250 kilowatts, find applications in village power, hybrid systems, and distributed power. Large turbines, with a power rating from 250 kilowatts to several megawatts, are used in central station wind farms and for distributed power generation. Classification of wind turbines, axis of rotation. On the basis of axis of rotation there are mainly two types: horizontal axis wind turbine, HAWT, vertical axis wind turbine, VAWT. Thanks for watching my video. If you liked it, please consider liking, commenting, and sharing with friends to help it reach more people. Your support is highly valued.